Okay.
Please do.
So I'm going to create a paper, I guess.
Yeah.
To start for some notes. Okay. And let me put it somewhere useful and send the link.
Okay.
I'll send it over over Zulip. Also here, just for convenience. And let me share this window. Okay. We'll start with this. So let me do one other thing. Just make sure I have my notifications turned off. Okay. Okay. So let's see. So I figured I'd start by, you just sort of explain a little bit about what the Rust rules are, since I figure you may not have messed with them too much. Like what we're trying to model from a user point of view, and get our terminology consistent and so on. We're trying to check, this is like quite a bit different in some sense than the stuff about Polonius we've been doing. It has nothing to do with regions or lifetimes, for example. We're just trying to check that all the data that you use is actually initialized. At least that's the way I think about it. There are different terminologies you can use. And this sort of, it's in a way, it's a very similar check to like, if you ever wrote Java code, there's some, maybe you haven't, maybe that's like I'm dating myself or something. But man, I haven't written it in a while either. Let's see, how does this work? Something like this, I don't know. Anyway, there's some check that would give you an error here, right? Uninitialized variable. This is a kind of standard check that people teach in compiler courses, for example. And we do a fancy version of that check. So the reason our check is fancier is, first of all, yes. First of all, yes, it would give an error in this situation, just like in the Java sort of case. But there are some other things that we can handle as well, right? So obviously, the most obvious one is something like this, where you moved out of V.
Yeah.
And I call that deinitialization. Basically, after you do a move out, what's left in that variable is just uninitialized memory from our point of view. And the other thing that we do, which is a bit subtle, is we track things at a finer level of granularity than just individual variables. So we might have like two vectors, and we can drop tuple.0. And of course, we'll get an error if we try to use tuple.0. But if we try to access tuple.1, that's okay. But we don't track things at infinite granularity because various reasons. There are some cases where we don't. So basically, there are various cases where it's not actually legal to deinitialize memory in the first place, right? So one of them is you can't move out from borrowed data. You can't move the referent of a reference. Another example that's a little more subtle is if a struct implements drop, you can't move fields of that struct. Ordinarily, you can move fields of a struct, just like with the tuple. However, if they implement drop, you can't. And the reason is, now it's sort of confusing and a little unclear, like, do we run drop? We can't run drop now because all the fields aren't there, so we can't invoke the destructor. But then what happened? Like the destructor just never runs? I don't know, it's just weird. So we don't allow you to do it. I think there's a third case, but I don't remember what it is. Oh, slices. Similarly, even if you have an array or a slice or something like this, we don't let you drop out of it because that would require us to sort of know. Well, let's come to the next point. We don't allow this. And why don't we allow it? Well, so there's a thing that's only tangentially related, which is like dynamic drop. So basically here we say we don't allow moves from all possible paths. So we also allow you to move, initialize. So dynamic drop, this was a hot debate some time ago. By now it's settled law, I guess. But the question is, if you have something like this, when does, let's suppose that in some particular run, something is false, this variable. Now the question is, well, let's suppose something is true, I guess, to start. So if it's true, then the vector is going to be dropped here. And obviously that means, you know, it would be an error to access v from the code here because it may or may not be initialized. But the question is, so the memory gets freed here. So everything's kind of fine in that case. The question is, if it doesn't go down that path, if it goes down this path, when do we free the memory for the vector? Do we free it sort of somewhere in this else branch? Or do we free it as we exit this block? And the answer in Rust is that v gets freed here, for better or worse. That's the semantics we chose. And the side effect of that is that actually v only maybe gets freed here, right? Because it depends on which path we took through the program. So we call that dynamic drop because it's dynamically decided whether we will drop the vector v as we exit this function. It basically depends on if somebody moved it already or not. And in the limit, or in cases like this, the compiler will actually insert a sort of flag, which is set to true when the thing is initialized, and then set to false here. You could not, of course, write code like this. We wouldn't allow you to yourself, but effectively, we write something like this to actually do the drop. So in the mirror, this is all that flag gets added after borrow check. So from borrow check's point of view, it doesn't exist. From borrow check's point of view, if we just look at the mirror, it's going to look something like v equals, you know, a new vector, whatever that looks like, some bunch of random code, you know, switch on something. This is like basic block 0. I don't know. I kind of forget what mirror looks like at this point in my life, but you get the idea. Stylized version of mirror. And so one thing to note is that, I'll just do it like this. Oh, I guess it would be like so. We don't really need this. No, I'll leave the else block in here as a basic block. So, say the math wrong. So from the compiler's point of view, this looks kind of like this. This isn't quite right, but you'll get the point. So yeah, not that it matters, but drop is a terminator in mir, so it always comes at the end of a basic block, and that's because it can unwind. But annoyingly, actually, something I would change if I could. But in any case, so right. So what you see is that actually in the mirror, as we see it, there are 2 drops for V, and it's certainly possible for one to reach the other, right? Because you can go from 0 to 1 to 3, and now you've got 2 drops. So mirror's kind of semantics is that you can drop the same thing multiple times, and that's okay. You can sort of imagine that the runtime semantics includes a flag for whether it's initialized or not, and drop has the semantics of checking this flag and then dropping only if it is, and then we later sort of lower that by making the flag explicit where it's necessary and otherwise not. Right, so after that big tangent, what does that have to do with this? Well, that relates to these arrays, because if we allowed you to drop from an array, we would have to remember which index you dropped and which indexes you didn't. And that means we can't just use Boolean flags. It had to be something more complicated. And so we didn't want to support that, so we just don't. There's a couple other situations, I think. The other one is you can't drop. Oh, well, no, you can. Never mind. There's something about enums and matching which doesn't really matter here. You can't sort of drop some parts of an enum and not others, but or we will drop all the rest for you is kind of what happens. In any case, all right. So come back to this. So this is what we want to. This is the analysis we want to implement. Basically, we want to give these errors when you try to move, or what borrow check currently does. It will give you errors when you try to move from things you're not supposed to move from. But more importantly, it'll give you errors when you access things that may not be initialized. And actually, these errors we probably won't do in Polonius, at least not to start. Maybe never, because they're not really. I mean, what I mean is the errors about moving from a path you're not supposed to move from. Those are like not very interesting. So. Oh, why is my screen sharing paused? I don't know. Has my screen share been paused this whole time?
Maybe, yeah.
Oh, no wonder.
I don't think it was. It just had a weird view.
Okay.
But it was following along on the paper document.
Well, somehow you followed. Okay, that's good.
Yeah. I told you otherwise.
So, all right. So that sort of made sense so far, I hope. Mm-hmm. So what does this analysis look like? Well, let's actually drop over to code a little bit. This analysis, so if you go to borrow check and we go over here, you'll start to see what we do somewhere. Okay, it's a bunch of code. So when we actually do the analysis, this part isn't too important, but, or it will be important, but it's not at a high level important, but there's 3 steps. We construct this move data, and I'm going to talk about that in a bit, but that's sort of more how it's implemented than the conceptual thing. Then we compute two important sets of bits, and one of them is called maybe initialized, and one of them is maybe uninitialized. That's here. And we compute a few, well, I guess there's 3. I'll explain why there's 3 in a second. There's one third set that is a little bit of a side step called ever initialized. And I'll explain that one in a minute. That's sort of a weird one, not as central. And so what these bits are is they're basically tracking what sets of paths have been or may be, as it says, initialized at a given point, and which ones may not be. And so the way we do this, so if you recall, I said that we allow you to, we have to track this not just at the resolution of, not just at the resolution of local variables, but also subpaths like tuple.0, right? And there could be like an infinite sort of set of potentially interesting paths. If you imagine like a recursive structure like so, yeah, you get the idea. And well, it turns out they would have to terminate in an option, actually, but nonetheless, there could be a lot of paths. Like you could imagine that if you just started like all the paths a user might name, there could be quite a lot. So what we actually do is we construct the paths that we actually see, and only those within the source function we're analyzing, right? So for this one, we might, well, first of all, we'll always make, we have this set of interesting move paths, and we're going to give each one an index. And first thing we do is we make one for every local variable, because that just makes our lives easier. So there'll be a path for tuple. But then we're going to analyze the program, and we're going to see, oh, the user actually accesses tuple.0. So I'll make a path for tuple.0. And then later we'll see that they access tuple.1. So we'll make a path for tuple.1. If it happened that they didn't ever access tuple.1, then we just would have no path for it. So
and if you have a dynamic access to the tuple, then you treat that as an access to the entire tuple, right?
What does it mean by a dynamic access to the tuple?
You can dynamically access the nth part of it, right?
Oh, no, you can't do that.
You can't do that, okay.
So for a tuple, you could access through a slice or something. But yeah, so basically we take the path that you accessed, or we go through and look at each path that appears in the function, and we could have construct one of these indexes. But we don't access every possible path. We only construct indices for paths that you actually could drop. So paths like this, star through a reference, or a field of a struct that implements drop, we're going to see later, we will never have what's called a move path for that. Because we don't really need to track the initialization of that, because it can't be de-initialized. So it's basically initialized if the parent path is initialized, and otherwise not, right? So that's what a move path is, essentially. It's just an index that maps to a path that you might have moved from, that you've used. And we have these are arranged in a sort of couple different ways, but one of them is a tree, so that you can go from the parent to each of the children and vice versa. So let me show you that. Or let me not quite show you that. The reason I'm talking about move paths is once we have indices for all these, now when we do these analyses, like is it maybe initialized? These are basically computing, these are data flow analyses, they're computing bit sets. So we now have bits to express them in terms of, right? There are sets of these indices. So maybe initialized, you might have, if we look at this function, you might say, okay, at this point, there's nothing initialized. At this point, we've initialized 0, 1, and 2 because by assigning to tuple, we also assigned to all the subpaths of tuple sort of implicitly, if that makes sense. And then at this point, we moved out of 1, so we only have 0 and 2 are maybe initialized, right? Makes sense. Okay. So let's look at this move path real fast. Just to be clear, or my plan for is I'll walk through what the code does today, and then I will sort of pivot to what part of this Polonius will do, which shouldn't take that long, I hope. So but we'll see how far we get. Right, so this gather moves, what this is actually doing is creating those move paths and also just indexing. It's kind of computing, in the Polonius sense, the base input facts from the program, actually. And if you, see if I can find where that code actually lives. I think this code lives in Dataflow, yeah. So this code is not part of borrow check, this move analysis code, and that's because it was initially written before we had the mirror borrow check. We still had to do this dynamic drop analysis, and it used a lot of this code. It was like the first consumer because it also had to do answer similar questions. Anyway, so the move paths. So this is in terms of the code, we have this move path index. That's just a new typed index that represents a move path. Let me just drop in some code links. So this is a new typed index representing a move path. And the actual move path is here. So you see that it contains a place. This is a mirror place, or what I've been calling path. In mirror, we called it place. Something else I might change someday, or I would possibly change. But anyway, so this is like, this is the mirror version of tuple.0 or whatever. So we're kind of interning them into these move paths. And then these 3 fields, these encode the tree. Not sure if you've seen this encoding of a tree before, but it's super useful. So this is a link to the parent, the index of our parent. This is a link to, or rather this one, is a link to our first child. And then there's a linked list. That's what the next sibling field is our child you can sort of go down the list, the siblings of the child. So this way you store, the nice thing about this encoding of a tree is you can store 2 fields per, if you ignore the parent for a moment, 2 fields per node, but you can sort of build an arbitrary size tree. You don't need to have like a vector, for example, a vector of children. So it's more condensed. Well, depends on your point of view. But in any case, that's how it's encoded. It's a linked list threaded through this next sibling. And you can kind of see that, like, oh, well, this is some code that walks up the parents of a path. That's very easy. You just get the parent and iterate, loading the next parent each time. But there's some other code, like, where is it? I don't know, somewhere or other that I don't see right now. Probably in another module. There'll be some code that like walks all the children for example, of a given index. And it'll do that by first load the first child, and then from there load the next sibling as you go. Okay, so that's what these move paths are. And where they're built, that's what I wanted to show you. So the first thing we do is this gather moves function, which is here. And all that does is it invokes this builder. So this builder is here. And what this is going to do is walk over all the statements and the terminators in the mirror and gather information about them by calling, gather statement, which invokes some visitor, which is the gatherer. And the gather statement will look, and it's basically looking for what are the effects of each kind of mirror statement. So this is what I meant by this is basically building up your Polonius facts, or what Polonius would call the input facts. So for example, here it says, okay, we have an assignment into place from ref file. First, create move path. What does that do? That will take this mirror place and create a move path corresponding to it. Mm-hmm. And we're going to look at this in a second. But if you remember, I told you that not all move paths, not all places have move paths because they can't all be moved out of. So this function doesn't always succeed, but here we don't care. So this function might give back an error basically saying this is not something that I can make a move path for. If it were like a field of a struct with drop. And then, where was I? Down here somewhere. All right. Then it's going to say, oh, like, for example, this is an assignment, so I'm initializing this place here. Therefore, I don't know what this initialization state thing is. Oh, this is some, you can kind of ignore that. That's a weird thing. So basically it's saying this gather init, this is going to add it. It's going to mark that at this location, we initialize this place, right? So let me jump back one moment. Oops, no. Just go back to here. So the move data, where am I? No, okay, fine. The move data that we're constructing, I should have talked about this actually, this is the thing called the move data. And I spent a lot of time talking about the move paths. So one of the big things that move data has is an index saying for each move path index, here's the actual move path data. But it also has all this other stuff, right? And this reverse lookup, that's just a map, I think, that helps you quickly map from place to move paths, sort of rather than searching linearly through this array. But this stuff, like moves and location map and stuff like that, this is detailing the effects. So the location map says at a given location, here are the paths that get moved out of from that location. And the way we do that is we give each time that there's a move, we create an entry in this vector which we call a move out, and it stores some information. It stores like this was the path that was moved, and here's where it was moved from. So actually, in Polonius sense, this would be exactly a set of facts, right? So the move data stores facts about the input source. It has the mapping from places to move paths. It also has like a list of moves or move outs, which I think you would kind of call like, I don't know what, I forget what our letters we used for these things. I'll call MP and P. So sort of saying there was a move out from this move path to this point. right? And then we have that data indexed by where the move occurs, so that we sometimes want to access it that way. So just like in Polonius, you end up with two versions of the same thing. You have the same here. And then similarly, we have mapped this way. If you want to know every place that a given path is moved, here's a mapping. Okay. They both just index into this vector, which has the data. And similarly, we have a list of inits. These are all the places that a path is assigned to. Right, so this path was initialized at this location, and some extra information, I don't know what that is. Let's store this. Let's make links to this. With me so far?
Yeah, I think so.
So that's what this data structure does. I guess I won't dig into the gathering except to say that it fills out all those fields. The one thing I did want to look at is the move path construction. It's not super exciting, but I suspect it will be relevant. So yeah, so this is the function that makes a new move path, I think. And note that we only ever create move paths in this first pass. There's other functions later that do the lookup, but we assume that we've sort of made all the move paths that are ever interesting in this first pass. And after that, it's just looking up. And so basically what it does is it what does it do? Okay, this code has changed a little bit. This is probably thanks to Santiago, who's been refactoring these things. So a place in Mir has a base, like a local variable usually, and then a set of projections, right? So this place.iterate, I think, this is the code I have never seen before, but this is what I think it does, invokes this function for each projection.
What's a projection? I don't.
Like a field, like if you have a.b.c, B and C are projections. They call it you're like projecting out from the base path. That's what it said. Okay. And so what does this do? So, or no, it looks like this is a list. Okay, so I guess it's iterable. Anyway, the point is we can sort of build this starting from one side and moving forward, right? And so we start with the base. I said that we always have, for every local variable, we have a path. We just make one. That's the easiest thing to do. You can always move out of a local variable, so that's fine. So we do that. Then we walk down each projection. So if you started out with A, then we're now looking at the B, if you have a.b.c. And we look at what was the type, what is the type of the thing we're projecting from? So if we're looking at a.b, we're looking at the type of A here. And we'll give some errors in some cases, right? So you can't move, for example, out of a borrowed pointer. So if we see that you're trying to build a move path that goes through a borrowed pointer, we'll just stop and return an error at that point. Right? So we will along the way, I think, have built up paths for all the leading up things that led up to that pointer, but we don't actually build one for the referent itself. Similarly, if an ADT is a struct, if this is a struct that has a destructor, we'll stop and so on, right? But otherwise we succeed. So we're going to first check if it already is in there or not. This is basically just look it up in the hash map. If it's not in the hash map yet, we'll construct a move path, and that's it, right? So that's how we do it. So then the main point is that this function basically builds all the move paths that it can, and then either gives you back an okay result if it got all the way through, or gives you an error if somewhere along the line it couldn't. And then that error, that's why you'll notice, you remember that code that said let underscore equals. So sometimes that error doesn't mean anything. Like if this code is not actually moving out from that path, it's just like initializing that path, that's fine. We don't need to have constructed all the paths. But if it is an actual move, we would report that error to the user. And then I think we just, I don't know what we do in terms of, well, we could look whether we actually generate a move out data structure or not. We may just ignore the move in that case. Probably that's what we do. That's what I would think would be good, if that makes sense. What is this? Don't do this. I lost my tab. Where did it go? Come back, tab. Okay. So, okay. So the point is, this is basically, we make one of these for every move that is a legal path. Okay. All right, so far so good. Then what do we do? I think enough about move building. Let's talk about how we actually use this stuff. I'm assuming you'll stop me if anything is confusing. So what we do now, once we've built this move data, now we know where the moves are, we know where the initializations are, then we do these data flow computations, right? And these are very analogous to, these are, of course, what we want to move to Polonius. And that's what that's doing right now is it's using this data flow framework, which is kind of a generic framework-y thing. And the idea of this framework is that you define, oops, wrong place. You define analyses like, let's see if I can find one. Well, the framework is going to be parameterized by a BD, or a bit denotation, which is basically what are we computing? Like there's a struct that corresponds to computing maybe initialized and a struct for maybe uninitialized. And that's what this BD is. And that's, you see we're building them here, right?
And this seems very similar to liveness, because you're basically tracking what can be or is potentially initialized at which points of the control flow graph.
That's right. It's essentially, so all of these are data flow analyses, right? They all work the same way. They have these kill and gen sets, and you propagate it around. It's just a matter of what do you consider a kill and what do you consider a gen. And that's exactly what this bit denotation thing is all about. So let's see if I can find where that is. Right, so for each of these, they're going to define this bit denotation, which has what is the index type. So this is like, and then a bunch of random stuff that's not that important, and then this stuff, which says, basically, we're going to call these callbacks as we walk the control flow graph, and they're supposed to add and remove things from the sets of what's present or not present, right? Okay. And so there's one that's like when you start the block, before the statement, when you execute the statement. And if we come up to data flow impulse, we'll see some of these things in action. So like maybe initialized, this is the, right, so maybe initialized places, this is the struct that does that analysis. There's some comments here, or where is it? Let's see, for maybe initialized. Okay, and then it implements bit denotation. Let's see.
Denotation? What does that mean?
What does denotation mean? To be honest,
yeah.
To be honest, I've never understood why this trait has that name. You'll have to ask Felix. But usually denotation is like something, you denote something when you reference it. So okay. I guess it denotes the bits. I don't know. Maybe gives meaning to, there's probably some. I would have called it something else, but I'm not sure my name would have been better. So just different.
There's a problem with these very generic things, right? It's,
right.
You can't name.
I think I would have called it analysis definition or something, but anyway. So That may or may not have been better though.
No, it's just as
See?
bad.
Exactly. Dataflow Operator. Anyway, whatever it is, you get the idea. It's a very generic thing. It's a data flow factory builder constructor. So I'm trying to find the interest. This is all like super generic code. There's somewhere I found earlier where it sort of bottoms out. But where is it? Here we go. Update bits. I think that's it. There's some helper functions. But in the end of the day, they kind of boil down to killing and genning. And you can sort of see that this code references that dynamic drop thing. These helper functions basically say, there was some stuff from the statement or terminator or whatever else that caused us to change the drop flag state for this path to either absent or present. And presumably present means there is a value present, and therefore we should gen the bit because we're maybe initialized. So like we want to include it if it's present and exclude it if it's absent, right? And maybe uninitialized is exactly reversed. But okay, that's how this code works. What we'll do I think what we'll do is, in Polonius we'll have like a move out and an init, and then the actual analysis is basically exactly the same as liveness. Just copy and paste it and put the right things in the right place, right? Like,
yeah. I've almost written a macro for that already.
yeah, you can make a macro for it.
Yeah, because we do already have a duplicate. Actually, I was starting to look into creating macros for that would have translated the more prologish or data logish thing into, but that turned out to be.
I've thought about that from time to time.
Yeah.
Seems complicated.
Yeah, that's what it does, right? The one you're borrowing the syntax from. I think they do that. But they generate C++ from the prologue, and then they embed that, and then you would have another language to maintain, which is a bad idea.
Yeah, and it's like sometimes we want to do tricks, and I don't know.
Yeah.
I decided not to do it at this point, but it is very tempting because it's
very tempting.
It's like almost trivial, but not quite. But yeah, you get the idea. So it's maybe initialized if it is actually initialized, and it's also maybe initialized if there's a predecessor or whatever, and it hasn't been moved, something like that. I guess one difference would be from liveness is these are forward analyses, not backwards. So, you get, so there'll be some CFG, PQ. Oops, damn it. How did this become a link? I don't know. Go away, link.
What is it? Oh, it's maybe it's
okay.
Yeah.
You get the idea.
Still,
We'll leave it alone. So let me think. What am I not telling you? So, right. Okay. One last thing. So I'm going to assume that you've figured out we're going to define some sort of maybe uninit, some sort of MPP thing here. Then the question is, what is an error? Like we can compute these in Polonius readily enough, but now where do we start to get errors? So when you see an access, this basically comes down to when you see an access to a path, it must not be maybe uninit, right?
Yeah.
And oh, let me point that out. So you'll notice that maybe init is not actually needed for your errors. The only thing we use maybe init for you've already come across, which is the drop dead, the drop liveness.
Yeah. Okay.
So drop liveness becomes something like, is dropped at point P and is maybe init at point P.
Yeah.
Which actually
this has to have.
Go on.
So this analysis has to happen before the liveness analysis because it's used in the live.
That's right.
Okay. Makes sense.
And I have to look. We can look, actually. Let's look right now. I'm trying to think. This might mean that we only need to compute maybe init for local variables. I forget how smart we are. We can come back to let's not worry about this just now. But we'll compute it for everything, but we might be able to optimize by doing less, or maybe we can get smarter. The point being, you know, if you've moved from one half of the tuple but not the other, I don't think we're smart enough to understand that only that half, like only the half that you haven't moved from is drop live and the other half is not. But we do some sort of smart things like that. I don't think we do that particular one, but I'm not sure. I can't remember. I have to look at the code. But this is the main error. And the way that this works in RustC, so we do this maybe uninit computation, and then we have this other thing. Where is this code? I forget which file. This, like, everything is in this file probably. There's a lot of code in this file. Let's take a look. Maybe uninit. Yeah. So there's some code in between the stuff I was showing you and this that I'm looking at right now that kind of walks over the mirror again. And along the way, we have this notion of flow state. Let me show you that. Flows new. So this is the top level code that's like the entry point to borrow check that we've been looking at, where it computes the move data, it computes the maybe inits, and you see that it does these kind of early. That's because they're needed for liveness. Then later, and then they just get dropped after that. Then later it computes the maybe uninits and a bunch of other random stuff, and it puts all of those things into this flows data structure. And that just means these are all data flow sets that we want to track as we are walking through the borrow check. We want to have their values sort of up to date. So at this statement, what is the set of uninitialized things? That's what this is. So it groups together the data flow analyses whose values should be up to date for the current point. And part of the reason we do it this way in this code is that we don't store all the values for all the points. We only store the values on entry to each basic block, and then we sort of recompute the intermediate states as we go, which is something that we don't do in Datafrog. And it would be nice if we can just never do that, because it's really complicated. But maybe we'll have to reproduce it someday. I don't know. Anyway, so then as we walk the data flow, we're going to call this check if full path is moved if we see a move, or no, if we see an access to a given place at a given location. These are looped together just for clarity, I think. Say that that's the span of this place. So what that does is it calls this helper. Let me leave a link here. It calls this helper move path closest to. And what that basically does is says, well, maybe a.b.c is not something we built a move path for because c is a field you couldn't move from. Then we want the longest path we can get. So if a.b.c doesn't exist, then a.b, maybe that exists. In the limit, a should exist. And this usually succeeds. You can see it can actually error because it's not always, the paths don't always begin with a local variable. They can begin with global variables too. But as long as it begins with a local variable, it should succeed because there's a path for every local variable. And then we can check if that's initialized. So essentially, yeah, if you access a.b.c, what's that?
How do you check the global variables? Because we don't compute.
We just don't. They're immutable. So they must be they're always initialized, and you can't move out from them, so they can never get uninitialized.
Right.
So, right, we basically find the closest move path we can and check that it is uninitialized or is not uninitialized.
Sorry, another question. Are the function arguments also treated as local variables, or how are they?
I think they're treated as local variables, but we generate them on entry as initialized.
Yeah, exactly. That's what I was.
Yeah.
Okay.
And yeah, the only special mere local variable that's the other mere local variable that's a bit special is there's a return slot, and that one would be never initialized, or it's certainly not uninitialized. Certainly not initialized on entry. So yes, access to a path must not be maybe an init. Right, and note, actually, it might be that, well, no, I was going to say it might be that if you access a.b.c, it might not exist for many reasons. Like, it might be that you can't move from that path. I think in principle, we could choose not to generate move paths for things that are never moved from, but are only accessed in other ways, because then they are initialized if the base structure is initialized and otherwise not. However, I think at moment we are simpler than that, and we just generate move paths for everything. So basically, the only reason that there would not be an exact match is, yeah, okay. So that's pretty much how the code works today. I think what Polonius wants to do, we want to add our base facts, which is going to be move out. So I guess we have a new atom, first of all, the move path.
Yeah.
And we have base facts, move out, move path point, and well, actually, there's initialize. Yeah, we could call these, depending, I don't know, we could debate the names. You could imagine calling it initialize and uninitialize, for example. Not sure if that's clearer or less clear. But it occurs to me that this is very similar to, if not identical to, a def in the liveness analysis.
Yeah.
The only real difference is the def is basically an initialize that's to a local variable and not some other kind of path. So
yeah,
like,
yeah. Oh, right, because we do the reverse analysis because we're looking for illegal access, not for, okay, yeah.
Right. Oh, there's something I left out. Well, I didn't leave it out, but it's relevant. If you have something like, if you have A equals foo, this is going to generate an initialized fact, but actually it might generate more than one, depending, right? So there might be A dot, like if there are subpaths, they're also being initialized. And there's some code in the, I think this logic is probably not I have to double check, but I think the gather moves logic is kind of already has this covered, the existing moves. In other words, there'll already be entries in the array for all the subpaths. But I'm not sure if that's true because actually that's probably not true. That probably can't be true. I realize now. Because you need to do two passes. You need to first generate all the move paths and then come back and figure out what all the subchildren are. You might not know them all at the time when you're, if you see what I mean, like when you see A equals foo, you may not yet have seen AWDC. So I think that expansion probably happens in the bit denotation impl today. I think we probably want to do it in the data log itself. So that implies there's probably another relation.
Yeah. Yeah.
Something
Because
like this.
Point calculation, yeah. So you want to do it, yeah. That makes sense.
Certainly, I didn't even talk about. I've sort of offhand mentioned Lark a few times. Lark was just a sort of different compiler, different language, but it had similar things. And I did this in Lark, and I remember that I put this logic in the Dataflow.
Yeah.
Anyway,
I tried to read the code. I understood the comments, but not the code. Yeah.
Well, the Lark code is. I'm not sure if you mean the Lark or the Rust code. The Lark code is kind of confusing also because that's like.
Yeah, the Rust code for Lark.
Okay.
But the one you linked from.
Yeah, I at some point wanted to go back and make it read beautifully, but anyway, you never have enough. So I was looking over it today. I was like, man, this Dataflow stuff. It's like so nice, but it's kind of right only. You have to be very careful documenting it. So anyway, these are probably your base facts. And then we can compute from these. Let's just start with maybe uninit, I guess. We'll deal with maybe init later because it's not relevant to errors. And well, we need some other thing, which is probably something like access, which is also similar to what liveness has, right? Which is like use the value from this move path. And similarly, foo of A is a use in liveness and an access. And similarly, accessing A implicitly accesses all subpaths. And so we have again a sort of transitive closure thing going on. So an error winds up being something like, there was an access to some move path MP that is either uninitialized or has an uninitialized child. Transitive. And then I think that's kind of it. That's the idea. Yeah.
I suspect that fact generation will be the hard part.
You think the fact generation will be the hard part?
Yeah, usually anything that happens in my experience now from working with this, I would say that the Rust things are the hard parts.
Yeah. This stuff is fairly straightforward. I think the one saving grace here is that we're actually kind of already generating facts. Like that move data structure is kind of already got everything you need. So you just sort of have to iterate over it and spit it out. I was just going to say the Lark type check, just for reference, I probably already linked to it, but just so I can, my own edification. Yeah, these are doing similar things, tracking this is tracking the uninitialized, right? we'll probably wind up, I don't think you should read this, but I'll probably go reread it and try to remember, because I suspect we're going to wind up computing all the same things. But one of the things that came up that I do remember is there's a lot of like phasing here. Because the Datafrog stuff likes to distinguish closed relations from iteration variables. You can see that I sort of, like there's a first path here that computes. I think this is saying overwritten is my version of initialize, but if you write to a given path at a given spot, then you also write to all the children of that path, right? And I compute that sort of as one thing and get a relation out of it, so that I can then later do leap joins and stuff like that with it. And similarly, if you access all the different ways to access a given path, this may not be relevant, but I'm sort of combining like, oh, it's a direct access, or it's a transitive access. So I computed the transitive relation, and then I can just kind of join them together, and so forth. So we may wind up trying to do stuff like that. But nonetheless, I think you are correct that the hard part will be the Rust code. I think that's kind of all I got in terms of giving a high-level picture. I imagine that you sort of have a feel for the drill by now. Probably we would approach it in this order, more or less. Start by adding the atom and generating the base facts, and then write the Polonius code. Speaking of which, I don't know, I haven't looked today, but I guess I need to start merging things, huh? Is this this is not ready, or is it ready for me to merge, or not yet?
It's ready for you to merge.
Okay.
And whenever that's ready, I've already done the work on rebasing the Rust one.
Sweet. Okay. Very cool. I will take a look.
I did the stupid thing and ran Rust FMT on some file, and that so now I get merge conflicts whenever anything happens upstream. I'm never doing that again.
Well, I do that a lot, but what I do is I do it in one commit.
Yeah.
And if there's a merge commit, I just throw away my version and rerun Rust format, and then that's the new commit.
Yeah.
However,
that might have been.
It's still annoying, but it's less annoying.
Yeah.
All right. Well, any last questions?
I have two last questions. One which might be easier than the other one, but let's take them in order of distance to topic. Okay, so I didn't quite understand when exactly something is maybe uninitialized. You skimmed over that part. And
yeah, really... that's a good point. Okay, so let's first start with the intuition. If we go back to this example, so let me remove all these drop flags. Or let me make a version that's clean without the drop flags. So if you look at this, here, V is initialized. Yeah, you get the idea, but I'll go through the exercise anyway. You could say that V is definitely uninitialized here. Here, V initialized. Yeah.
Okay, yeah. So it means if there's an uninitialization on the path to a block in the control flow graph, then it's maybe uninitialized, of course, yeah.
Yeah, pretty much if there's
Yeah, without a subsequent initialization.
Yes, that if an uninit can reach the point without an interrupting init. Yeah, and that's exactly what you want to express in this relation here or something, right? Like uninit can reach P without an init in the middle. Yeah, we could go through the exercise, but as you say, it's basically cutting and pasting from liveness. And that's it. Next question.
Okay, the next question was, I saw the input fact universal regions, and I don't understand what it is. What is a universal region?
Oh, yeah. Okay. I don't like that terminology anymore, and I've been trying to move away from it. But what it refers to is the named lifetimes on the function parameter. And the reason I called them the universal is that they're universally quantified, meaning that you have
4 points.
Yeah, you don't know what tic A is, but it's some set of things. Yeah, I think for the purposes of Polonius, they're not very different from any other region except that they're sort of live all the time.
Yeah.
And they're a little special in some.
Okay.
I have been trying to move towards the terminology of free regions because they're free, but that's also not amazing. But anyway.
In what sense are they free?
They are free in the sense that, so do you know the free and bound terminology?
Yeah.
They're not bound in the function body. Like they're region names that they kind of reference things from the outside, so they're free in that sense.
Yeah.
It's not the best, but it's at least consistent. That or placeholders, that's my other term of choice. But anyway.
Okay, that was both my questions. So now
Great.
I understand lecture. No, I'm sure I don't, but it's a good start.
Cool. All right. Well, let me know. I'll try to answer questions. Talk to you later.
Yeah, see you.